For as long as humans have studied the cosmos, one question has hovered at the edge of imagination. What if anything existed before the Big Bang? Modern cosmology treats the Big Bang as the beginning of our observable universe of space-time, and the matter and light within them, yet the same physics hints at deeper possibilities that may lie beyond this boundary. Today we explore how science carefully approaches a question that may never have a final certain answer. If you enjoy calm journeys to the frontiers of cosmology, please subscribe and share and tell us in the comments which idea about before the Big Bang fascinates you the most. Thank you for watching. Now let's begin. The present universe stretches out in every direction, filled with galaxies, clusters and faint backgrounds of light, and astronomers treat this whole visible scene as a kind of map that hints at a deeper story. Telescopes sensitive to different colors and energies record galaxies that are near and bright galaxies that are far and faint, and some that are so distant that their light has been stretched by expansion into long, soft wavelengths. From these careful surveys, a picture forms of an observable universe, a region of space from which light has had time to reach Earth since the universe first began to expand. And even this simple idea starts to raise the question of what existed outside this slowly growing sphere before the familiar story of the hot Big Bang phase. In this map, the nearest galaxies drift apart at a gentle pace, while the most remote ones recede at great speeds, and this pattern fits with a universe that has been expanding for about 13.8 billion years. The rate of this expansion measured in kilometers per second per megaparsec. A large unit of distance equal to about 3 million light-years is known as the Hubble constant, and different methods of measuring it, from the brightness of distant supernovae to the motion of galaxies in large clusters, build an interlocking web of evidence that the cosmos is not static. A static universe, one that simply sits unchanging, would leave a very different pattern of positions and motions on the sky. But the real sky shows a dynamic, evolving structure, and this evolution hints that the visible universe emerged from earlier, denser conditions that seem to call for an explanation beyond the simple idea of everything beginning at one instant from nothing. The observable universe is often described as a bubble, not because it has a sharp physical edge, but because there is a horizon defined by time. Light can only travel so far in a finite duration. The most distant galaxies that can now be seen lie tens of billions of light-years away, and yet their light has taken almost the full age of the universe to reach Earth, because space itself stretches during the journey. This means that the galaxy map is also a time map. Looking farther out is the same as looking further back in time, and each ring of distance carries information about a younger stage of cosmic history. Near the present day, there are massive clusters of galaxies, webs of filaments and voids that occupy vast spans of space, all shaped by gravity acting over billions of years. Farther out, the galaxies appear younger, less clustered and more blue in colour, signalling stars that are newly formed. At even greater distances, the light comes from galaxies that are just assembling from gas clouds, collapsing for the first time, and from a universe that is only a small fraction of its current age. This gradual change with distance allows cosmologists to reconstruct parts of the past without leaving the present, but it also shows that the hot, dense early phase was itself a special state that does not simply fall out of the laws of physics without further questions. Modern instruments do more than take pictures of individual galaxies. They measure subtle patterns in how galaxies cluster together on very large scales, charting a cosmic web whose size can reach hundreds of millions of light-years. These patterns carry the imprint of sound waves that move through the early plasma, leaving preferred separations between galaxies that act as a kind of standard ruler. By measuring how this scale appears at different distances, astronomers test models of how the universe has expanded over time and they find strong support for a cosmos that began hot and dense and has been thinning and cooling ever since. Yet this success introduces a puzzle. The standard hot Big Bang description works well once the clock is set to a tiny fraction of a second after that phase begins, but it does not explain why the universe on those earlier slices of time is already so smooth, so nearly flat in its geometry, and so delicately balanced in its energy budget. The sky on large scales is almost the same in every direction, and space is very close to Euclidean, meaning that parallel lines stay parallel over enormous distances, and the total amount of matter and radiation is matched closely to the rate of expansion. If the universe had started from random or generic initial conditions, these things would not be expected. Instead, the cosmos appears to begin in a state that looks prepared. This sense of preparation is not a poetic flourish. It is a description of how sensitive the later structure is to the early conditions required by the standard equations of cosmology. A small change in density at the beginning would give either a universe that recollapses quickly or one that flies apart so fast that galaxies never form. A modest increase in unevenness would lead to a sky that is patchy and irregular rather than smooth. Observations do not show this. They show a universe that is almost but not perfectly uniform, with just enough small variations to grow into galaxies and clusters. The map of the observable universe therefore does more than confirm that a hot Big Bang happened. It forces the recognition that some process acting before the hot phase arranged the conditions in a very specific way. As cosmologists refine the measurements using satellites that measure ancient background light and surveys that scan millions of galaxies, the uncertainties shrink and the picture of an early tuned state grows clearer. With each new data set, the question becomes harder to ignore. If the hot Big Bang phase already assumes a smooth, nearly flat, finely balanced universe, then the true origin story may lie in whatever physical mechanism set up that state. The gentle, persistent evidence drawn from the sky today points away from the idea of an absolute beginning and towards some prior phase, perhaps cold and dominated by a special kind of energy that prepared the conditions from which the Big Bang then emerged. The cosmic map of galaxies is only one layer of evidence for an early hot phase. Another more ancient signal arrives not from single objects but from every direction at once, as a soft bath of microwave radiation that fills all of space. This radiation is known as the cosmic microwave background, and it is often described as fossil light because it last interacted strongly with matter when the universe was very young, then travelled freely for almost the entire age of cosmic history. In the present, it appears as a nearly uniform glow at a temperature of about 2.7 degrees above absolute zero spread evenly across the sky. When sensitive instruments are pointed outward, this glow shows up no matter where they are directed, and when known local sources are carefully subtracted, what remains is this smooth background, a quiet reminder that the universe was once far hotter and denser than it is today. The existence of such a background was predicted as a natural consequence of a hot Big Bang model in which the early universe is a plasma of free electrons, protons, and light scattered in all directions. As the universe expands and cools, there comes a time when electrons bind to protons to form neutral atoms. Once that happens, light no longer scatters as frequently and can travel long distances without being absorbed or deflected. The cosmic microwave background is this released light still arriving now after billions of years of travel. It carries with it detailed information about the state of the universe at the time when atoms first form, when the cosmic age is only a few 100,000 years rather than many billions. Because this light comes from every direction, the sky becomes a kind of shell, a surface of last scattering on which the early universe writes a record of its conditions. When satellites such as the Planck Observatory map this radiation with fine resolution, they reveal that the background is not perfectly uniform. Instead, the temperature of the glow varies slightly from place to place by an amount of only a few parts in 100,000. On a false colour map, these tiny variations are painted as patches and streaks, but in reality they are gentle ripples in density and temperature. Regions that are slightly denser show up as slightly cooler or warmer spots, and over time those small differences grow under gravity into galaxies' clusters and the large-scale structure seen today. In this way, the cosmic microwave background offers a direct bridge from the nearly smooth early universe to the intricate web of matter that exists now. The pattern of these ripples is not random. It carries specific signatures of sound waves that move through the early plasma, compressing and rarefying the gas in a way that leaves characteristic peaks and troughs in the spectrum of temperature variations. By studying these patterns, cosmologists can infer the total amount of ordinary matter, dark matter, and radiation present at that time, as well as the overall curvature of space. The results are striking. Space appears to be nearly flat on large scales, meaning the geometry is very close to what one would draw on a sheet of paper rather than on the surface of a sphere or a saddle. The universe appears to be extremely uniform with only tiny deviations from exact smoothness. The mixture of matter and radiation inferred from the data lines up with what is needed to produce the structures observed today. All of this reinforces the picture of a hot Big Bang followed by expansion and cooling. Yet, as in the galaxy map, success brings deeper questions. The cosmic microwave background does not merely say that the universe was once hot. It shows that the initial conditions of that hot phase are very special. The near flatness implied by the data means that at early times, the total energy density of the universe has to be tuned with great precision relative to the rate of expansion. The almost perfect uniformity across regions of the sky that in a simple Big Bang model without additional ingredients would never have been in contact, raises the horizon problem in a sharp form. Distant regions separated by more than light could have travelled in the time available, still come to close agreement in temperature and density. The tiny but non-zero level of fluctuations also sits in a narrow range that allows structure to grow without becoming wildly irregular. These features suggest that something acts before the release of the cosmic microwave background to smooth, flatten, and gently perturb the universe in a consistent way. The rapid expansion phase called inflation is proposed as that something. In an inflationary model, a form of energy stored in the vacuum drives a brief period of very fast expansion, stretching any initial irregularities over scales far larger than the observable universe. Regions that are once in close contact get pulled so far apart that they now lie beyond each other's horizons, which explains how the entire visible sky can share a common temperature. Quantum fluctuations of the field that powers the rapid expansion become frozen as tiny density variations, providing the seeds for the ripples seen in the background, and later the seeds for galaxies. When inflation ends, the energy driving it converts into particles and radiation heating the universe and setting up the hot plasma phase that leads directly to the cosmic microwave background that is seen today. In this picture, the background light does more than confirm a hot Big Bang. It preserves the imprint of an earlier, colder, more abstract period when the vacuum itself dominates the dynamics of space. The data from Planck and other experiments are broadly consistent with the predictions of simple inflationary models such as the overall flatness and the nearly scale-free pattern of fluctuations, though subtle details continue to be studied. There are also tentative features and slight anomalies in the sky map, such as regions with somewhat lower power on the largest scales or small asymmetries in opposite directions that may or may not be significant. At present, they are hints rather than firm discoveries, but they keep open the possibility that the rapid expansion phase is more complex than the simplest models suggest. If so, the cosmic microwave background might carry concealed clues about the structure of the vacuum, the behavior of the inflaton field, or even interactions with other regions beyond the observable patch. The history of the observable universe can be traced backward from the present web of galaxies into a time when matter and light behave very differently, and the standard Big Bang model provides a clear set of steps for this reconstruction. Starting from mature galaxies rich in heavy elements, stars and planets, cosmologists wind the clock back in their equations and allow gravity, pressure and radiation to reverse their roles. Galaxies that are now far apart draw closer together. Clusters and filaments shrink. The average density of matter rises and the overall temperature of space increases. Stars that once shone as stable nuclear furnaces are replaced in the picture by an earlier gas of hydrogen and helium glowing with intense radiation. At a few billion years after the beginning of the hot phase, galaxies are still taking shape, and the tallest clusters have not yet assembled. Rolling further back, the universe reaches an age of hundreds of millions of years, and the first stars ignite in dark gas clouds, producing the earliest heavy elements and sending out ultraviolet light that slowly clears a fog of neutral hydrogen. Before this period of star formation, the universe is a simpler, more uniform sea of gas, almost entirely hydrogen and helium, with tiny variations in density inherited from even earlier times. The temperature is higher, the typical distances between atoms are smaller, and the light that fills space is more energetic. Continuing inward in time, the reconstruction arrives at an age of only a few 100,000 years. At this stage, the universe is hot enough that atoms are just beginning to form from a plasma of free electrons and nuclei. When electrons combine with nuclei, mostly protons, to make neutral hydrogen, light decouples from matter and begins the long journey that later appears as the cosmic microwave background. The snapshot preserved in that background shows a cosmos that is already very smooth on large scales, with only slight variations in density, and that fact becomes a boundary condition for any account of what happened before. The Big Bang model reaches still further back with the help of nuclear physics. When the universe is only minutes old, its temperature and density are such that light atomic nuclei can form in a process called primordial nucleosynthesis. In this brief era, collisions between protons and neutrons build deuterium-helium and small amounts of other light nuclei. The predicted ratios of these elements depend delicately on the density of ordinary matter and the expansion rate. Observations of primordial helium and deuterium in ancient gas clouds match the values calculated from the model, giving strong support to the idea that the universe passed through this hot, dense state. These same observations also help to fix the amount of ordinary matter, which in turn feeds back into models of galaxy formation and large-scale structure. The cosmic microwave background, the clustering of galaxies and the relic abundances of light elements together form a consistent picture in which a single hot plasma evolves into the rich cosmos that is seen now. Beyond this point in time, as the clock winds closer to the first fractions of a second, the picture becomes more abstract. Events are packed into extremely short intervals, and changes that once took millions of years now occur in less than a heartbeat on the cosmic timeline. Matter and radiation are so energetic that distinctions between different particle species blur. Quarks and gluons, the building blocks of protons and neutrons, move freely in a quark-gluon plasma. As the universe expands and cools, these particles become confined inside protons and neutrons, which later assemble into nuclei during nucleosynthesis. The physics of these processes is tested in particle accelerators on Earth, where temperatures and densities approaching those of the early universe can be created in brief collisions. Results from these experiments support the broad outline of how the hot plasma behaves, but they do not by themselves reveal what set up this extreme initial state. To move even closer to the start of the hot phase, cosmologists rely on equations that combine general relativity with known particle physics, and then extrapolate well beyond the range in which direct experiments are possible. The density and curvature of space-time rise toward values where quantum effects can no longer be ignored. The temperature of the plasma surpasses the energies reached in accelerators, and theories that unify the basic forces into a single interaction become relevant. In these conditions, small differences in the assumed initial state have large consequences for the later universe. A slight change in overall density, a modest increase in the unevenness of matter, or an alteration in the early expansion rate can produce a cosmos that either collapses quickly, expands too fast for galaxies to form, or shows a sky that is much more irregular than the one actually observed. From the point of view of the equations, many other early universes are allowed, yet the real one occupies a narrow region of possibilities. The standard model of cosmology therefore treats the earliest slice of the hot Big Bang as a starting surface, on which the universe is already expanding, already nearly the same everywhere, already very close to flat in its geometry. The model then follows the evolution forward with great success, matching the cosmic microwave background, the abundances of light elements, and the growth of structure. When it is run backward, the same framework leads reliably from present galaxies to a dense, rapidly expanding plasma, but it does not by itself explain why that starting surface has the particular properties it does. The reconstruction ends at a wall of high temperature and high density, where the equations invite a description of what came before, while the model itself simply begins. At this boundary, just before the era of primordial nucleosynthesis, and long before atoms form ideas such as a rapid inflationary expansion, begin to enter proposing that the hot Big Bang marks a transition from an earlier phase rather than a unique origin. As the hot Big Bang framework is pushed back toward its earliest moments, it begins to reveal a set of precise puzzles that do not show up in everyday experience, but become clear when the whole universe is treated as a system to be explained. One of these puzzles concerns how uniform the cosmos is on very large scales. The sky in microwave light shows almost the same temperature in every direction, with only tiny fluctuations. In the simple Big Bang picture, without any additional early phase. Distant regions of the sky are so far apart that going back in time, there has never been enough time for light or any signal to cross from one to the other before the moment when the cosmic microwave background is released. These regions lie outside each other's particle horizon, the boundary that marks how far causal influences can travel at light speed over the age of the universe up to that time. Yet despite this limit, they display nearly the same temperature and density. In everyday terms, widely separated patches behave as if they have communicated and reached equilibrium, even though the standard model without modifications does not give them any opportunity to do so. This mismatch between what the equations allow and what the sky displays is known as the horizon problem. It does not call into question the existence of the hot phase itself, but highlights that if that phase is all there is, the initial conditions must be chosen with great care. A second puzzle concerns the geometry of space. General relativity allows the universe to have positive curvature, negative curvature, or almost no curvature at all. Positive curvature corresponds to a closed geometry, somewhat like the surface of a sphere where parallel lines eventually converge. Negative curvature corresponds to an open geometry, similar in some ways to a saddle, where parallel lines spread apart. Observations, especially those that study the pattern of fluctuations in the cosmic microwave background, indicate that the actual universe is extremely close to flat, with curvature so small that it is consistent with zero within current uncertainties. When the Big Bang equations are run backward, this near flatness today implies that in the very early universe, the ratio between the actual energy density and the critical density required for exact flatness must have been set extraordinarily close to 1. any small deviation would grow over time, leading by the present era, either to large positive curvature with a universe poised to recollapse, or to large negative curvature with a rapidly expanding, very diffuse cosmos. The fact that neither extreme is seen means that the early universe must begin in a state where this ratio is tuned to a value very near unity. This sensitivity is known as the flatness problem. It suggests that either the initial state is special in a way that the simple model does not explain, or some process acts early on to drive the universe toward flatness regardless of its starting conditions. A third issue arises from particle physics. Many theories that extend the known forces and particles predict the existence of very heavy exotic relics, such as magnetic monopoles or other massive states that would be produced in large numbers in a very hot early universe. In a basic Big Bang model that starts arbitrarily close to a singular state of extremely high temperature, these relics are expected to be abundant. However, searches for such objects have found no convincing evidence that they exist in the present universe. This absence forms the monopole problem. Either the initial temperature never reached the regime where these relics would be generated in such quantities, or some later process diluted them to a negligible level over a vast volume of space. The combination of horizon flatness and relic problems points to a common theme. The standard hot Big Bang evolution, when applied from a chosen starting surface onward, works very well to match the observed abundances of elements, the background radiation, and the large-scale distribution of galaxies. Yet the same framework offers no internal reason why that starting surface should already be so smooth, so nearly flat and so free of exotic relics, while still containing exactly the right amount of small irregularities to grow into cosmic structure. The equations of general relativity do not forbid such a state, but they do not single it out either. It occupies a narrow region in the wider space of mathematically allowed initial conditions. Small shifts away from this region would in most cases produce universes that do not resemble the one that is observed. This situation encourages the idea that the hot Big Bang phase is not truly the beginning, but instead a later chapter in a longer sequence of events. In that sequence, there may be an earlier epoch in which the dynamics of space and fields act in a way that naturally smooths out irregularities, pushes curvature toward flatness, and reduces the density of unwanted relics. When cosmologists look at the cosmic microwave background and at the distribution of galaxies, they see not only confirmation of the hot Big Bang picture, but also evidence that these conditions were established with a precision that is difficult to attribute to arbitrary choice. The puzzles are sharpened by the fact that the tiny remaining irregularities are just large enough to form galaxies, but not so large as to break the near uniformity on large scales. The amplitude and pattern of these fluctuations follow a gentle, almost scale-free behavior, which suggests that they arise from a physical process rather than being imprinted by hand at the start. In this way, the puzzles of horizon flatness and relics, together with the measured properties of the small fluctuations, point beyond simple initial conditions and motivate the search for mechanisms that operate before the hot plasma era. Among the proposed mechanisms, one of the most influential concepts is a period of rapid expansion that reshapes the early universe in a short time and leaves behind an almost uniform, nearly flat and lightly perturbed state, from which the familiar Big Bang evolution proceeds. In many modern cosmological models, the carefully prepared conditions of the hot Big Bang emerge from an earlier stage in which space itself undergoes an extremely rapid, almost explosive expansion, driven by a special form of energy. This stage is called the inflationary phase, or more simply inflation, and it is introduced not as an extra decoration, but as a way to let the dynamics of the universe, rather than a fragile choice of starting point, generate the smooth, nearly flat and gently perturbed cosmos that later evolves into galaxies and clusters. In this picture, the very early universe is dominated by the energy of a field that fills space often imagined as a kind of scalar field whose value can change from place to place. When the field sits in a high-energy configuration, its contribution to the stress energy of the universe acts in a way that makes the expansion rate almost constant, rather than steadily slowing down as in a radiation or matter-dominated case. Under these conditions, the size of the universe grows exponentially, which means that in equal intervals of time, distances between freely moving points double again and again. Even if the region that will become the observable universe starts off very small, perhaps far smaller than an atom, a series of many doublings during inflation can stretch it to a size much larger than the entire visible cosmos today. This repeated doubling has several important consequences for the puzzles described earlier. Any initial curvature of space becomes diluted as the overall radius of curvature grows enormous compared with the size of the observable patch, so that the local geometry appears almost perfectly flat. Any initial unevenness in the density of matter or radiation is smoothed out as regions that once contained fluctuations are stretched beyond the observable horizon. Exotic relics such as magnetic monopoles, if they are present at all, are spread so thin that their density within the visible region becomes effectively zero. After a sufficient period of rapid expansion, the patch of space that will later host galaxies becomes almost uniform in density, nearly flat in geometry, and very simple in its contents, dominated by the slowly changing energy of the inflationary field. The details of how inflation begins, how long it lasts, and exactly how it ends depend on the underlying particle physics model. In many simple treatments, the field starts high on a potential energy curve and gradually rolls down as time passes, rather like a ball slowly moving down a shallow hill, though the mathematical description uses field values rather than literal positions. As the field rolls, the energy density driving the rapid expansion changes only slowly, and the universe continues to inflate. Eventually, the field reaches a region where its energy can decrease rapidly and convert into particles and radiation. When that happens, the inflationary phase ends, and a process often called reheating takes place in which the energy stored in the field is transferred into a hot bath of ordinary and dark matter and radiation. This newly created plasma forms the starting point for the hot Big Bang description, with a temperature and density high enough to allow the standard sequence of nuclear reactions, recombination, and structure growth to unfold. In this way, the Big Bang becomes not an absolute beginning, but a transition between a vacuum-dominated inflationary phase and a radiation-dominated hot phase. Inflation does more than smooth and flatten the universe. Because the inflationary field is treated as a quantum object, it experiences small random fluctuations in its value at every point in space. During inflation, these quantum fluctuations are stretched by the rapid expansion from microscopic scales to astronomical scales. Once stretched beyond a certain size, they effectively freeze, becoming classical variations in the local energy density. These tiny differences are the seeds from which later structure grows. Regions with slightly higher density start to collapse under their own gravity once the universe is no longer dominated by the inflationary field, while regions with slightly lower density become the voids between clusters. The pattern of these primordial fluctuations is predicted in many simple inflationary models to be almost scale invariant, meaning that its statistical properties change only slowly with the size of the region considered. Observations of the cosmic microwave background indeed show a fluctuation spectrum very close to this form, with small deviations that may carry information about the precise shape of the inflationary potential and the behavior of the field as it rolls. This match between theory and data is one of the main reasons inflation is taken seriously as a description of what the universe was doing just before the hot Big Bang phase. At the same time, inflation remains an effective framework rather than a fully derived theory. Different choices of field potential, different couplings to other fields, and different assumptions about the initial state lead to different variants of inflation, many of which are consistent with current observations. Some versions predict detectable signatures such as particular patterns of gravitational waves imprinted on the polarization of the cosmic microwave background, while others predict signals that are too small to measure with present instruments. Satellite missions and ground-based experiments that try to detect or constrain these signatures aim to distinguish among models and perhaps rule out broad classes of inflationary scenarios. Regardless of the outcome, the basic idea that a rapid expansion phase can transform a complicated or generic early state into the special conditions required for the hot Big Bang provides a concrete response to the horizon flatness and relic problems. It also raises new questions because a mechanism that can stretch space and dilute irregularities so effectively can in principle operate for a very long time perhaps, without a natural global end, and this possibility leads directly to ideas in which inflation is not a brief event that happens once everywhere, but an ongoing process that continues in some regions while ending in others. In the inflationary picture, the smoothness and flatness of the observable universe are not imposed by hand, but arise from the way a single field dominates the early dynamics of space, and the small imperfections that remain are traced back to quantum behavior in that field. In ordinary conditions, quantum fluctuations are confined to microscopic scales and average out when large regions are considered. During rapid expansion, this is no longer the case. The field that drives inflation fluctuates slightly in value from point to point, and because space is expanding exponentially, regions that once were close enough to share information are pulled far apart in a very short interval of time. When a fluctuation is stretched beyond a characteristic scale set by the expansion rate, it stops oscillating and effectively freezes into a small difference in the local energy density. In intuitive terms, what began as a tiny quantum uncertainty in the field becomes a fixed classical perturbation in the fabric of the inflating universe. Over the course of many e-foldings of expansion, countless such perturbations are laid down on different scales, forming a spectrum of density variations that later serve as the seeds of structure. After inflation ends and the energy of the field converts into a hot plasma of particles and radiation, these frozen perturbations show up as regions that are slightly overdense or slightly underdense compared with the average. In the overdense regions, gravity gains a small advantage over pressure, and matter begins to drift inward. In the underdense regions, matter flows away, leaving behind volumes that will become cosmic voids. As time passes and the universe expands more slowly, the initial pattern of small differences grows in contrast. Overdense patches collapse into bound structures, first into small halos, and then into larger complexes that merge into galaxies and clusters. The underdense regions expand faster than average, carving out the vast low-density spaces between filaments. The detailed statistical properties of this pattern, such as how strong the fluctuations are on different length scales, can be predicted from simple inflationary models and compared with observations of the cosmic microwave background and the large-scale distribution of galaxies. The close match that is seen supports the idea that quantum fluctuations during inflation are the origin of all later cosmic structure. The treatment of these fluctuations uses both general relativity and quantum field theory. In this framework, the inflating universe is described by a smooth background metric representing the average expansion plus small perturbations that represent variations around this average. The inflationary field is similarly split into a homogeneous part that drives the overall dynamics and a fluctuating part that moves randomly due to quantum effects. The equations governing these perturbations can be written so that each Fourier mode corresponding to a wave of a particular wavelength evolves independently while its physical size is smaller than the characteristic horizon scale set by the expansion rate. In this regime, the mode oscillates like a quantum harmonic oscillator. When the expansion stretches it so that its wavelength exceeds the horizon, the oscillations cease and the amplitude becomes fixed. This process repeated for many modes as the universe inflates produces a nearly scale invariant spectrum in which the amount of power in fluctuations changes only slowly with scale. Careful analysis also shows that the perturbations generated in this way are almost but not exactly Gaussian, meaning that their statistical distribution is close to a simple bell curve with only small corrections. Measurements of the cosmic microwave background temperature fluctuations and of the related polarization pattern are consistent with this prediction. They show no strong signs of non-Gaussian features that would indicate more complicated interactions or multiple active fields during inflation. This agreement constrains many alternative models but does not uniquely determine the underlying physics. Variants with slightly different potentials, additional fields or non-standard kinetic terms can often be arranged to give similar power spectra over the range of scales that observations currently probe. Future measurements, such as more sensitive maps of the polarization of the background or surveys of the distribution of matter through gravitational lensing, may be able to distinguish more clearly between possibilities. For now, the data confirm that the pattern of primordial fluctuations behaves just as expected for quantum seeds laid down in a rapidly expanding spacetime. When thinking about what existed before the Hot Big Bang, this quantum origin of structure has a subtle implication. It suggests that the vacuum state of the inflationary field, the state that would normally be called empty, is not a simple void, but a medium with definite properties that can fluctuate, and under the right conditions can drive expansion and generate particles. The energy density associated with this vacuum behaves differently from ordinary matter or radiation. It remains nearly constant as space expands instead of thinning out. This is what allows inflation to continue for many foldings once it starts. At the same time, quantum fluctuations can nudge the field in different directions in different places, changing the local duration and character of the rapid expansion. In some regions, the field may roll down its potential quickly in inflation and reheat into a hot Big Bang phase. In other regions, it may linger on the high-energy plateau, keeping inflation going for much longer. The result is a picture in which the inflating space does not end everywhere at once, but instead gives rise to isolated bubbles where inflation has stopped embedded in a larger background where it continues. Within each such bubble, a universe like the observable one can form complete with its own microwave background and pattern of galaxies, while beyond the bubble wall, the inflationary process carries on, and the underlying vacuum continues to fluctuate and spawn new regions where local conditions can differ in detail. As long as the average vacuum energy stays high enough in at least some parts of the larger space, the process of rapid expansion feeds on itself, and the question of what existed before the Big Bang in one bubble becomes linked to a broader picture in which inflating space quantum fields and many possible cosmic patches coexist for an extended period, rather than ending at a single moment. When the inflationary idea is extended beyond the simplest picture, it naturally leads to a scenario in which the rapid expansion does not stop everywhere at once, but continues in some regions while ending in others. In this extended view, sometimes called eternal inflation, the universe is no longer described as a single patch that inflates for a brief interval and then settles into a hot Big Bang phase. Instead, the underlying space keeps stretching in many places, driven by the energy of the inflationary field, while in scattered locations, that field slips into a lower energy state and releases its energy into particles and radiation. Each such location becomes a bubble of hot plasma, expanding into the surrounding inflating space. Inside, the bubble conditions resemble those of the familiar Big Bang, with a hot dense beginning followed by cooling nucleosynthesis recombination and the gradual growth of structures. Outside, the rapid expansion continues carrying the bubble away, and at the same time making room for new bubbles to form. The driving mechanism for this behavior lies in the quantum fluctuations of the inflationary field itself. Although the field tends on average to roll down its potential energy curve, the quantum nature of the field means that in some regions it is briefly pushed upward rather than downward. In such regions, the energy density remains high for longer and the local rate of expansion stays large. Because the space in those regions expands so quickly, their volume grows faster than the volume of regions where the field has already decayed and inflation has ended. Even while bubbles are forming and exiting the inflationary regime, there are always other parts of the universe where the field is still high and the total inflating volume continues to increase. In this way, the process becomes self-sustaining. Inflation ends locally in individual pockets, but it never ends everywhere. At very large scales and over very long times, there is always an inflating background in which new hot regions can arise. Each bubble that forms in this vast inflating environment is effectively a new universe, at least from the point of view of observers who arise within it. The interior of a bubble undergoes its own hot Big Bang evolution, with its own microwave background, its own pattern of galaxies, and its own history of structure formation. The bubble has a boundary, a wall, where the hot interior meets the still inflating exterior, but that boundary recedes at nearly the speed of light, and is quickly carried far away by the ongoing expansion. Observers who form deep inside the bubble can never see beyond a limited region around them, and that region looks just like an entire universe, with a horizon and age, and a specific set of physical parameters. The larger inflating space with its endless production of bubbles lies forever beyond their observational reach. In such a setting, the question of what existed before the Big Bang in one bubble does not receive a single global answer. Instead, the Big Bang of that bubble is understood as the thermalization event that follows the local end of inflation. Before that event in the same region space is part of the inflating background dominated by the energy of the inflationary field. Even earlier or elsewhere, the field may have been in slightly different configurations, and random quantum fluctuations may have pushed it around in ways that change local properties. The global picture becomes that of a multi-stage process, an inflating space seeded with quantum fluctuations, occasionally transitioning into hot phases within growing bubbles, with inflation persisting in the surrounding regions. There is no single time slice that marks an absolute start. Instead, there is a network of local starts where different bubbles experience their own Big Bang-like transitions. This eternal inflation framework is flexible enough to accommodate a wide variety of underlying particle physics models. The potential energy landscape of the inflationary field can have multiple plateaus and valleys, each corresponding to different possible vacuum states, with different energy densities and perhaps different effective physical constants. Quantum fluctuations allow the field to sample this landscape moving from one plateau to another or tunneling through barriers between regions. When a transition occurs, a bubble of the new vacuum forms and expands. Inside, the energy difference between the old and new states is converted into particles and radiation, igniting a hot Big Bang phase. The detailed properties of that phase, such as the temperature at reheating the spectrum of light fields and the rates of various interactions, depend on exactly where in the landscape the field comes to rest. From the standpoint of observers confined to a single bubble, only the local outcome is accessible. The measured values of the speed of light, the strength of gravity, and the masses of familiar particles appear as fixed features of nature. The cosmic microwave background displays a pattern of fluctuations that reflects the specific inflationary history within that bubble. The large-scale structure grows under the influence of the particular balance of dark matter and dark energy present there. Yet the mathematics of eternal inflation allows other bubbles to exist with different histories and potentially different physical settings separated by distances so great that no signal can ever cross between them. The multiverse in this sense is not a collection of separate universes placed side by side in an external space, but a single inflating space-time in which widely separated regions evolve quasi-independently after passing through different transitions. This view changes the role of initial conditions. Instead of specifying a single finely tuned starting state that leads uniquely to a universe like the observable one, the theory describes a process that continually explores many possibilities. Inflation smooths and flattens whatever region it dominates, and quantum fluctuations ensure that some parts of the inflating space last longer, form different transitions, or settle into different vacua. The conditions that hold inside any given bubble, including the one that contains the observable universe, then arise as one outcome among many. When cosmologists ask what existed before the Big Bang in this context, they're effectively asking about the properties of the inflating background and the rules that govern how bubbles form, evolve, and perhaps collide. Bubble collisions are one extension of this idea that has been studied in detail. If two bubbles form relatively close together in the inflating background, their walls may eventually meet. The collision can produce a complicated pattern of energy and fields in the overlap region, potentially leaving observable imprints in the cosmic microwave background of one or both bubbles. Researchers have searched for specific signatures such as circular features or directional asymmetries that could indicate a past collision. So far, no clear evidence has been found, but the possibility remains a subject of ongoing work, because any such detection would provide rare information about regions beyond the naive horizon. Even without direct signs of collisions, the existence of eternal inflation would mean that the observable universe is part of a larger, constantly developing structure in which Big Bang-like beginnings occur repeatedly in widely separated zones. In the eternal inflation picture, each bubble that forms has its own history, but the underlying laws that govern how fields behave and how space-time curves are assumed to be the same everywhere. Some theoretical frameworks, however, suggest that even those basic ingredients may differ from bubble to bubble. In such scenarios, the multiverse is not merely a collection of separate hot Big Bang regions that share identical physics, but a vast ensemble in which the effective constants of nature can vary from place to place. The speed of light, the strength of gravity, the masses of particles, and the detailed properties of fundamental forces are described in these models by parameters that depend on which vacuum state the underlying theory inhabits. The inflating background then explores a landscape of possible vacua. When a region makes a transition into one particular vacuum, a bubble forms, and the physical constants inside that bubble take on the values associated with that part of the landscape. The observable universe would then be a single realization from this broader set of possibilities. Fine-tuning questions become especially sharp in this context. Many features of the observed cosmos appear to rely on delicate balances between different ingredients. Stars can burn steadily for billions of years, only because nuclear reaction rates, particle masses, and the strength of gravity fall into a range that allows fusion to proceed in a controlled way, rather than running away explosively or failing to ignite. Elements such as carbon and oxygen, important for complex chemistry, are produced in stars through reaction chains that depend sensitively on the spacing of nuclear energy levels. The formation of galaxies and clusters requires gravity to be strong enough to overcome the expansion in overdense regions, while the overall expansion rate must not be so fast that matter remains too diffuse for structures to condense. The presence of a small but non-zero dark energy density in the present universe accelerates the expansion, yet its value is many orders of magnitude below the natural scale suggested by simple quantum field estimates. If that energy density were much larger, and positive structures would be pulled apart before they could form, if it were large and negative, the universe could recollapse quickly. From the standpoint of a single universe with fixed parameters, these coincidences raise the question of why the constants take values that allow long-lived stars, heavy element production, and the emergence of complex structures rather than values that lead to barren or short-lived worlds. In a multiverse with varying constants, the question takes a different form. If the inflationary process populates a wide range of vacua, each with its own set of effective physical parameters, then most of the resulting bubbles might have constants that do not allow galaxies stable stars or heavy elements. In those bubbles, the hot Big Bang evolution would still occur, but it would lead to universes that are simple in structure, short in duration, or dominated by featureless radiation and dilute matter. A smaller subset of bubbles would by chance occupy regions of the landscape where the constants produce a richer outcome with stable nuclear burning chemical complexity and long eras in which structures can form and persist. Observers who arise in such regions would then measure physical constants that lie in the narrow band compatible with their own existence. From their point of view, the constants appear finely tuned, but in the larger ensemble they are simply typical of the subset of bubbles where complex structures are possible. This way of reasoning does not explain why the landscape has the structure it does, nor why the rules that generate it take their particular form, but it offers a way to understand why the observable universe sits close to the boundary between very different possible behaviors. Some candidate theories of fundamental physics, especially those that attempt to unify all forces, naturally give rise to large families of possible vacuum states. Additional spatial dimensions may be compactified, meaning curled up into shapes too small to detect directly, and each distinct shape can lead to different effective constants in the lower dimensional world that emerges at large scales. Fields that take on different expectation values in these compact directions change couplings and masses in the extended dimensions. Fluxes threading through compact cycles can stabilize different configurations. The result is a theoretical landscape with a huge number of metastable vacua, each corresponding to a distinct set of low-energy physical laws. Eternal inflation then provides a mechanism for realizing many of these vacua in different regions of a single larger spacetime, where the field configuration tunnels or rolls into one valley of the potential a bubble with one set of constants forms. Where it chooses another valley, a bubble with a different set of constants appears. The inflating background persists, so this exploration of the landscape can continue for very long times. From the point of view of cosmology, the detailed mathematical structure of the landscape is less important than the qualitative outcome that many effective universes can exist with different properties. The observable universe is then tied not only to the question of why a hot Big Bang occurred, but also to why that Big Bang inherited exactly the combination of constants that it did. Measurements of the cosmic microwave background of element abundances and of galaxy clustering probe one point in the landscape, revealing the physics of this particular bubble, while theoretical studies of high-energy models sketch how other bubbles might differ. Even without direct access to those other regions, the possibility that they exist shapes how cosmologists think about initial conditions. Instead of trying to derive the observed constants as unique predictions of a fundamental theory, some approaches focus on explaining the statistical distribution of vacua and on estimating how often different types of bubbles form in the inflating background. In that view, the Big Bang that gave rise to the observable universe is one event in a much larger process in which inflating space quantum fields and a landscape of vacua together determine which kinds of cosmic histories can unfold. In some approaches to fundamental physics, the universe that is observed with telescopes is only part of a larger structure that includes extra spatial dimensions beyond the familiar three. In these models, ordinary matter and forces such as electromagnetism are confined to a three-dimensional surface, while gravity and perhaps other unseen fields can extend into additional directions. The three-dimensional surface is often called a brane short for membrane, and it can be embedded in a higher dimensional space that is sometimes described as the bulk. The observable universe then corresponds to the world on one brane, where galaxies, stars, and radiation move along the surface, but do not leave it, while the bulk provides room for other branes to exist and move. This picture allows new ways to think about what might have existed before the hot Big Bang phase, because interactions between branes in the higher dimensional bulk can act as triggers for violent events within the branes themselves. In particular, some cosmological models propose that a collision between branes can inject energy into the three-dimensional surface in a way that closely resembles a Big Bang. To see how such scenarios address the question of origins, it is useful to sketch the basic ingredients. A higher dimensional theory may include several branes each with its own confined matter and radiation suspended in the bulk. The branes can oscillate, and in some cases approach and separate from one another along the extra dimensions. When two branes draw near, the fields that live on them can interact strongly, and energy can be transferred from the relative motion in the bulk into excitations on the branes. If the geometry and interactions are arranged appropriately, a close approach or collision can heat the branes to extremely high temperatures, filling them with a dense plasma of particles and radiation. For an observer living on such a brane, the event would look like a hot beginning followed by expansion, cooling, and the later formation of structure, much like the familiar Big Bang evolution. The difference is that in the brane picture, this beginning is not an absolute start of all reality, but one episode in the longer motion of branes within the bulk. Before the collision, the branes already exist, the bulk already has structure, and time already flows. The hot Big Bang is then reinterpreted as the aftermath of an interaction in a higher dimensional setting. Brane collision models have been developed in several forms. In some versions known as ekpyrotic or cyclic scenarios, the universe on a brane undergoes repeated phases of contraction and expansion, with each cycle triggered by a renewed approach and collision between branes. During the contracting phase, the energy density on the brane can become dominated by a stiff form of matter, or by fields that smooth out in homogeneities, so that by the time of the next collision the brane is again nearly uniform and flat. The collision then heats the brane, creating a new hot phase that resembles a Big Bang, and after the collision the branes separate and move apart in the bulk. The expansion that follows can last for billions of years, during which stars and galaxies form live, and in many cases die while the branes gradually slow down, turn around and begin to move toward each other once more. In such a framework, what is called the Big Bang in the observable universe is just one link in a long chain of events, and there may have been many previous cycles before the current one. The question of what existed before the Big Bang is answered in part by pointing to an earlier cycle with its own contraction, collision, and reheating. These scenarios also make use of ideas from inflationary cosmology, but in a different way. Instead of a rapid expansion phase that begins from an arbitrary early state and smooths it out, the ekpyrotic phase relies on slow contraction, driven by fields on the brane or by the influence of neighbouring branes. This slow contraction can suppress anisotropies and inhomogeneities, bringing the brane to a nearly uniform state before the collision. Quantum fluctuations during this phase can generate perturbations in the energy density that later seed structure in the expanding phase, leading to a spectrum of fluctuations in the cosmic microwave background that is similar in some respects to the one predicted by inflation. The details differ, such as the exact shape of the power spectrum or the expected level of primordial gravitational waves, and these differences provide ways to test whether a brane collision or a simple inflationary phase better describes the earliest accessible stages of the universe. Observationally current data favour simple inflation in many analyses, but they do not completely rule out more complex alternatives, so brane-based models remain part of the discussion. The presence of extra dimensions has further implications for what may lie beyond the observable universe. If gravity can spread into the bulk while ordinary matter remains confined to the brain, the strength of gravity on the brain can depend on the shape and size of the extra dimensions. Small changes in the separation between brains or in the geometry of the bulk can alter the effective gravitational constant or the behavior of dark energy on the brain. In some constructions, the accelerated expansion observed today arises from the slow motion of brains or from the relaxation of fields in the bulk tying the far future of the universe to the same higher dimensional dynamics that shape its earliest hot phase. In this way, brain models naturally connect questions about the origin of the Big Bang with questions about the long-term evolution of cosmic acceleration. From the perspective of higher dimensional theories, the observable universe is then a local feature within a larger space, and the hot Big Bang marks the conversion of energy from brain motion or brain interaction into radiation and matter on the brain. The older and wider bulk with its network of brains and fields forms the stage on which such events occur. Asking what existed before the Big Bang in this context leads directly to the study of how brains move, how they are created and destroyed, and how their collisions distribute energy. The answer is no longer a single time slice, but a description of an extended higher dimensional environment in which Big Bang-like events can happen more than once and in more than one region, each leaving behind a hot expanding universe on a brain that for its inhabitants appears to be all there is. In parallel with inflationary and brain-based pictures, another family of ideas treats the Big Bang not as a unique event, but as one moment in a repeating sequence of cosmic phases. In these cyclic or bouncing models, the universe goes through periods of expansion and contraction, with transitions between them that can resemble a hot Big Bang. The earliest versions of such models imagined a simple oscillation where a closed universe expands from a dense state, slows under its own gravity, turns around and recollapses to a big crunch, after which a new expansion begins. In practice, this simple picture faces difficulties because entropy, the measure of disorder, tends to increase from cycle to cycle. Radiation and matter left over from earlier cycles would accumulate, making each new expansion larger and longer than the last. Over many cycles, this growth would blur the idea of a truly repeating universe. Modern cyclic and bouncing scenarios borrow tools from more recent physics to address these issues while still keeping the central idea that a Big Bang-like event can be preceded by a contracting phase, rather than by nothing at all. One class of models uses a slow contracting phase to smooth and flatten the universe before a bounce. In these ekpyrotic scenarios, a field with special properties dominates during contraction, causing anisotropies and inhomogeneities to decay rather than grow. The universe becomes more and more uniform as it shrinks, approaching a state in which space is nearly flat, and the energy density is dominated by the ekpyrotic field. Quantum fluctuations of this field generate small variations in density, which can later seed structure in the expanding phase. Near the bounce where contraction ends and expansion begins, the energy stored in the field is converted into radiation and ordinary matter, creating a hot plasma similar to the one that appears just after the Big Bang in standard cosmology. For an observer who lives long after the bounce, the visible history would look much like that of a universe that began in a hot Big Bang, even though in this picture, the hot phase follows from a previous contraction, rather than from an absolute beginning. Another group of bouncing models draws on attempts to quantize gravity itself. In classical general relativity, when matter and radiation are compressed beyond a certain point, the equations predict a singularity where curvature and density become infinite and the description breaks down. Quantum gravity approaches, such as loop quantum cosmology, modify these equations at very high densities. Instead of a singularity, the theory can produce a maximum achievable density above which gravity becomes effectively repulsive. As the universe contracts toward this critical density, The repulsive effect grows and eventually halts the collapse, turning it into a bounce. The universe then re-expands, passing smoothly through the moment that would have been a singularity in the classical theory. In such a framework, what appears as the Big Bang in the expanding branch is the continuation of a previous universe that was contracting. The detailed behavior of perturbations across the bounce and the way in which quantum geometry effects influence the power spectrum of fluctuations depend on the specific implementation, but the general message is that an earlier phase can replace the notion of a beginning at infinite density. Matter bounce models share some of these features, but focus on different ingredients. In these scenarios, a universe dominated by a form of matter with particular properties contracts from a large dilute state toward a dense configuration, while quantum fluctuations generate a nearly scale invariant spectrum of perturbations during the contracting phase. At high density, new physics causes a bounce, after which the universe enters an expanding radiation-dominated era, similar to the one in the standard Big Bang model. The pattern of fluctuations carried through the bounce can then show up as temperature variations in the cosmic microwave background and as seeds for galaxy formation. By adjusting the details of the contracting matter and the bounce mechanism, these models aim to reproduce the observed features of the sky without invoking a long inflationary phase. All of these cyclic and bouncing constructions share a common attitude toward the question of what existed before the Big Bang. Instead of treating the hot dense state as the first moment of time, they place it in the middle of a longer timeline. Before the hot phase, there is either a period of contraction on the same side of the bounce, or a previous expansion followed by collapse in an earlier cycle. The Big Bang is then the interface between phases, not the creation of the entire cosmic arena. The price of this extension is the need for new physics to control the contraction and to regularize the would-be singularity. Fields with unusual equations of state corrections from quantum gravity or interactions inherited from higher dimensional theories are invoked to ensure that anisotropies do not grow without bound and that the bounce occurs smoothly rather than catastrophically. These models also need to account for the observed acceleration of the present universe. In some cyclic scenarios, the current dark energy-dominated phase is interpreted as part of the cycle. The accelerated expansion thins out matter and radiation, smoothing the universe and diluting structures before a future contraction. In others, dark energy is a temporary feature that will eventually decay, allowing gravity to reverse the expansion. The same component that now drives galaxies apart would in that later stage give way to dynamics that pull them together. The specifics differ from one model to another, but the general link between early and late time behavior is a recurring theme. The properties that make a bounce possible, such as special fields or quantum corrections, can also influence how the universe evolves on very large timescales, so that the distant future and the distant past are tied together in a single repeating pattern. From the standpoint of observation, cyclic and bouncing models compete with inflation-based scenarios by making alternative predictions for the fine details of cosmic structure. They may predict different levels of primordial gravitational waves, different shapes of the fluctuation spectrum on the larger scales, or subtle, non-Gaussian features in the distribution of temperature variations on the sky. Current data place constraints on these possibilities, ruling out some versions while leaving room for others. As measurements improve, especially in polarization maps of the cosmic microwave background and in large-scale surveys of galaxies, it becomes possible to test whether the universe more closely follows a simple, inflationary expansion from a prepared state, a bounce from an earlier contraction, or some hybrid of these ideas. In these tests, the range of allowed early universe histories narrows and cyclic, and bouncing models are refined, altered, or discarded according to how well they reproduce the delicate structure seen in the sky. As the reconstruction of the early universe approaches the first tiny fractions of a second after the hot phase begins, the densities and temperatures involved reach values where the familiar description of space-time as a smooth geometric stage is expected to break down. General relativity treats space-time as a continuous fabric whose curvature responds to energy and momentum, and quantum field theory treats particles and forces as excitations on that background. Both frameworks work extremely well in their own domains, but they are built on different assumptions. At energies near the Planck scale, where the typical length is of order 10 to the power of minus 35 meters, and the characteristic time is around 10 to the power of minus 43 seconds, quantum fluctuations of the geometry itself become important. In that regime, the smooth metric of general relativity can no longer be taken as an exact description. Instead, space-time must be treated as a quantum object subject to uncertainty and superposition, in the same way that particles are. The earliest accessible instants of the hot Big Bang lie not far above this Planck era, so any complete account of what existed before the Big Bang has to pass through this domain, where the familiar concepts of space and time start to blur. The search for a quantum theory of gravity aims to provide a coherent description of this regime. Different approaches make different choices about what to keep and what to modify. Some begin by trying to quantize the gravitational field in close analogy with how other fields are quantized, promoting the geometry to an operator, and writing equations that describe its quantum states. Others embed gravity into a larger framework that includes extended objects such as strings or higher dimensional branes, with the hope that familiar space-time emerges as an effective description at large scales. Yet others propose that space-time is not fundamental at all, but arises from a deeper network of discrete building blocks, or from patterns of quantum entanglement in an underlying system. Despite their differences, these approaches share a common expectation that at Planckian energies the continuous picture of space-time must give way to something more granular or more abstract. In some loop-based models, for example, the geometry of space is represented by networks of finite links and nodes, with areas and volumes quantized in discrete units. In such pictures there is a smallest meaningful scale, below which the notion of distance loses its conventional meaning. When the universe is compressed to volumes near this scale, the effective behavior of gravity can change. Instead of the attractive force of classical general relativity continuing unchecked into arbitrarily high densities, quantum corrections can make gravity repulsive at very small scales. This can turn what would be a singular collapse into a bounce, allowing a previous contracting phase to pass smoothly into an expanding one. Other approaches that treat space-time as emerging from entanglement in a more fundamental quantum system suggest that near the Planck era, the degrees of freedom that later appear as points and distances are not yet organized in a way that resembles a classical geometry. Time itself in such views is not a basic parameter running independently in the background, but a property that emerges alongside space as certain correlations become robust. In either case, the language of a singular origin at a precise time becomes less appropriate. Instead of a single point where densities diverge, there is a region where the familiar continuum description fails, and some deeper structure takes over. String-inspired models offer another way to think about the Planck regime. In these theories, the basic excitations are not point particles, but extended one-dimensional objects whose typical size can be close to the Planck length. The vibrations of these strings correspond to different particles and fields at low energies, including the graviton, the quantum carrier of gravitational interactions. Because strings have finite size, physical quantities that would diverge for point particles can be softened, and certain types of singular behavior can be avoided. In scenarios where the early universe is described by a gas of strings and higher dimensional branes, the evolution near the would-be Big Bang can involve phases in which extra dimensions expand or contract symmetries between large and small radii are explored, and dual descriptions trade high temperatures for low temperatures in non-intuitive ways. The hot Big Bang phase that later produces the cosmic microwave background may then arise from a transition between different string-dominated phases, or from the decay of unstable configurations in the higher dimensional theory. These candidate quantum gravity pictures remain incomplete in many details, but they share the implication that the Planck era is qualitatively different from anything that follows. In later epochs, from nucleosynthesis to recombination and galaxy formation, space-time can be treated as a smooth expanding backdrop and matter, and radiation can be described by familiar fields. In the Planck regime, the distinction between background and excitations is blurred. Geometry fluctuates, causal structure may not be fixed, and the concept of a single time coordinate that labels all events may be replaced by a more relational description in which only correlations between observables are meaningful. The Big Bang singularity that appears in classical extrapolations marks the point where the older description ceases to be reliable, not necessarily a literal beginning of all physical processes. Because the Planck era lies far beyond the reach of direct experiments, clues about its nature must be sought indirectly. One avenue is to study how different quantum gravity models propagate perturbations from the Planck regime into later times. If certain approaches predict specific signatures, such as a distinct pattern of primordial gravitational waves, subtle departures from the nearly scale invariant spectrum of fluctuations or small non-Gaussian features in the cosmic microwave background, these can be compared with observations. Non-detection of a predicted signal can rule out some versions, while detection of unexpected features might hint at new physics. Another path is to examine black holes where strong gravity and quantum effects meet in a way that may echo conditions in the early universe. The evaporation of black holes through quantum processes, the entropy associated with their horizons, and the apparent holographic relation between bulk physics and lower dimensional boundary descriptions all suggest that space-time gravity and quantum information are tightly linked. Lessons drawn from these systems feed back into models of the Big Bang and of possible pre-Big Bang phases. In many of these frameworks, the question of what existed before the Big Bang is reframed. If time and space emerge from a more basic quantum structure, then asking what came before a certain moment may be like asking what lies north of the North Pole. The familiar coordinate simply does not extend beyond a certain region. Alternatively, if quantum gravity replaces the singularity with a bounce, then the answer may involve a prior universe that was contracting toward high density before rebounding into the current expansion. If space-time is part of a larger, higher dimensional manifold, then the Big Bang may correspond to a local event within that manifold, such as a transition between vacua or the formation of a new region. In all these cases, the Planck era acts as a bridge between the effective hot Big Bang description and a deeper level of structure in which the usual notion of a beginning might not apply in the ordinary sense. Seen from the present, the observable universe carries only faint traces of this domain. The cosmic microwave background shows no direct imprint of fully quantum geometric behavior, but its smoothness, its tiny fluctuations, and the absence of certain pathologies already suggest that some mechanism tamed the extremes that would otherwise arise from a naive extrapolation to infinite density. The same is true of the large-scale distribution of matter and the measured acceleration of the universe. They do not reveal the underlying quantum gravity theory, yet they set boundary conditions any such theory must respect. As models of Planck scale physics are refined, they must reproduce the successful predictions of general relativity and quantum field theory at lower energies, while modifying them in just the right way, at the highest energies to avoid singularities, and to allow a coherent extension of cosmic history past the formal beginning. In this way, the Planck era becomes a key focus for attempts to connect the observable universe, with its galaxies and background radiation, to whatever larger structure or longer story may exist beyond the reach of direct observation. While ideas from quantum gravity focus on the earliest instance of the hot phase, another line of investigation looks outward in space rather than inward in time, and asks how large the universe might be beyond the part that can be observed. The observable universe is defined by the distance that light has been able to travel since the expansion began. Light moves at a finite speed, and the universe has a finite age, so there is a horizon around any given point beyond which events cannot yet have sent signals. For observers in the present epoch, that horizon encloses a region whose radius is measured in tens of billions of light years. Within this sphere, galaxies and background radiation can be mapped, and the story of cosmic evolution can be reconstructed back to the hot plasma that filled space when the universe was young. Outside this region, light has simply not had time to arrive. The question of what lies beyond the horizon is therefore not answered by direct observation, but by inference from the properties of the part that can be seen. One of the main clues about the larger universe comes from measurements of spatial curvature. The geometry within the observable region can be probed using several independent methods, such as the pattern of fluctuations in the cosmic microwave background, the distribution of galaxies, and the way distant objects of known size appear on the sky. Together, these measurements indicate that space on large scales is extremely close to flat. In a perfectly flat universe, parallel lines remain parallel forever, and simple Euclidean rules for triangles and volumes hold exactly. In a curved universe, those rules are slightly altered. The fact that observations match the flat case to high precision implies that if there is any overall curvature at all, its radius is much larger than the radius of the observable sphere. This leaves two broad possibilities. One is that the universe is finite but so large that the part that is seen is only a small patch on a much bigger hypersurface, perhaps wrapped in a complicated topology, with identifications that repeat on scales far beyond current horizons. The other is that space is truly infinite, extending without bound in all directions, with the observable universe as a small region in an unending expanse. Another set of clues arises from the statistical properties of the cosmic microwave background. If space were finite with a size not much larger than the observable region, light travelling around the universe could in principle produce repeated patterns on the sky, and correlations between temperatures in widely separated directions might show specific signatures. Detailed searches for such patterns have not found convincing evidence that the universe wraps around itself on scales close to the horizon size. The absence of these signals pushes the minimum size of any finite topology to scales significantly larger than the observable sphere. In simple inflationary models, the picture is more straightforward. The rapid expansion during inflation stretches any initial patch of space so much that by the time inflation ends, the part that will become the observable universe is a tiny region within a vastly larger domain. In many versions, inflation lasts long enough, or continues eternally in some regions, that the total volume of space becomes effectively infinite. From the standpoint of everyday experience, an infinite universe is hard to visualize, but in the equations of cosmology, it is a natural possibility. A spatially infinite universe filled with matter and radiation, according to the observed average densities, can still have a finite age and a finite horizon. Only a finite region has been in causal contact since the beginning of the hot phase, even if space extends without limit. Each observer then inhabits a bubble of visibility surrounded by a much larger, possibly endless environment. Within that bubble, conditions look homogeneous and isotropic on large scales, just as the cosmic microwave background and galaxy surveys indicate. Beyond it, the same average conditions may continue or they may vary in ways that are linked to physics at very early times. In inflationary and multiverse scenarios, for example, different regions beyond the horizon can inhabit different vacuum states with slightly different effective constants of nature, while still sharing a common origin in an earlier inflating background. Even if the universe is not infinite in the strict mathematical sense, it can be so large compared with the observable patch that for all practical purposes the distinction is difficult to test. A finite universe whose linear size is many times larger than the radius of the horizon would be observationally almost indistinguishable from an infinite one. No signal sent in the present epoch would ever return after circling the universe, and no pattern from multiple circumnavigations of light would show up in the background radiation within any realistic observation time. In such a setting, the key point for the question of what existed before the Big Bang is that the hot phase in the observable region need not correspond to a global beginning. It can instead be a local event that affects only a limited domain within a much larger space. The rest of the universe, whether finite or infinite, may have its own history that does not start or end when the local hot phase does. This perspective is reinforced by models in which inflation is eternal, or in which brain interactions trigger localized heating events. In eternal inflation, the inflating background can itself be spatially infinite, with bubble universes forming at random locations and times. Each bubble contains a region that undergoes a hot Big Bang-like evolution, but the global inflating space continues elsewhere. In brain models, the higher dimensional bulk can extend far beyond the brain that hosts the observable universe, and collisions or other processes on different brains can occur independently of events on this one. In both cases, the part of reality that can be observed corresponds to a single patch within a broader structure, and the Big Bang marks the start of a particular thermal history in that patch, rather than the emergence of all space and time. From the observational side, current data primarily constrain the geometry and composition within the horizon. They show that on average, space is very close to flat that matter, and dark energy fill it in specific proportions, and that the pattern of fluctuations follows simple statistical rules. They do not yet reveal whether space beyond the observable region is finite or infinite, uniform or varied, or future surveys that map galaxies to greater depths measure gravitational lensing on very large scales or detect subtle correlations in the cosmic microwave background may tighten the bounds on curvature and topology, but they will still confront a horizon beyond which direct information is unavailable. As long as this limit persists, the wider universe remains partly hidden, and theories that treat the Big Bang as a local event in a much larger, possibly unbounded space continue to frame how cosmologists think about the connection between the visible region and whatever lies outside it. The story of what existed before the Big Bang is closely tied to the story of how the universe behaves long after that hot phase, and one of the most important discoveries about the present cosmos is that its expansion is not merely continuing but accelerating. Measurements of distant supernova explosions which serve as standard candles show that galaxies at large distances are dimmer than they would be in a universe whose expansion is slowing under gravity alone. Combined with observations of the cosmic microwave background and the clustering of galaxies, these data indicate that a large fraction of the total energy density today is in a form that does not clump into stars or galaxies, and that exerts a kind of negative pressure. This component is called dark energy. Unlike ordinary matter which thins out as the universe expands, dark energy behaves in a way that keeps its density nearly constant over time. As space grows, new space seems to come with the same amount of dark energy per unit volume, so the total amount of dark energy in a given moving region increases. In the equations of general relativity, such a component causes the expansion rate to speed up. The effect is gentle on human timescales, but dominant on cosmic ones. In a universe where dark energy remains constant, the expansion gradually outruns the pull of gravity on ever larger scales, and structures that are only marginally bound eventually fall victim to the accelerated growth of space. The presence of dark energy changes how the future is expected to unfold. In a cosmos without it, the long-term fate would be decided by the balance between matter density and expansion speed. If matter density were high enough, gravity could eventually halt the expansion and reverse it, leading to a recollapse and perhaps a big crunch. If matter density were too low, the universe would expand forever, but at a rate that slows over time, with galaxies gradually growing farther apart yet still visible in principle after very long intervals. With dark energy that behaves like a cosmological constant, the outcome is different. As the universe ages, matter and radiation become ever more dilute, while the density of dark energy stays almost unchanged. Eventually, dark energy dominates completely, and the expansion approaches a phase of nearly exponential growth. Galaxies that are not gravitationally bound to the local group recede faster and faster. Light emitted from them struggles to make headway against the stretching of space, and is redshifted to longer wavelengths until it becomes undetectable. Over very long periods, only the nearest bound structures remain visible from any given location, and the cosmic microwave background is stretched to wavelengths so long that it no longer plays a practical role as a bath of radiation. The universe becomes cold and empty in the sense that average particle densities fall towards zero, even though dark energy continues to fill every region of space. On smaller scales, stars burn through their nuclear fuel and leave behind white dwarfs, neutron stars, or black holes. Over still longer times, even these remnants can cool, evaporate, or decay. The detailed timeline depends on many factors, including the stability of protons and the behavior of black hole evaporation. But the broad picture is that in a dark energy-dominated universe, with a constant density, the future is one of continued expansion, cooling, and dilution. This long-term trend is sometimes called a heat death, not because the universe becomes hot, but because energy becomes too thinly spread to power new complex structures on large scales. In such a scenario, there is no natural mechanism within the visible region for reassembling matter into a new, hot, big bang. The universe does not cycle back to high density under its own gravity. Instead, it moves further away from any state that resembles the early hot plasma. Alternative descriptions of dark energy allow different fates. If dark energy is not a pure cosmological constant, but a field that slowly evolves over time, its energy density and pressure can change. In some quintessence models, the field gradually rolls down a potential, and the acceleration of the universe may weaken or even reverse in the far future, possibly allowing a return to matter-dominated behavior or a gentle recollapse under certain conditions. In other models, dark energy density increases with time, driving an ever faster expansion that could in extreme cases overcome even local gravitational and electromagnetic binding, pulling apart galaxies, stars, and eventually smaller structures in a so-called Big Rip. Modified gravity theories offer yet another angle in which the observed acceleration arises not from a new form of energy, but from changes in how gravity behaves on very large scales. Each of these possibilities carries its own implications for the distant future, and each rewrites the late chapters of cosmic history in a different way. Current observations favour a model close to a simple cosmological constant, but the uncertainties still leave room for more complex behaviour. The role of dark energy in the question of what existed before the Big Bang comes from the way its properties echo those of the inflationary field in the early universe. Both act as forms of vacuum energy that remain roughly constant as space expands, and both drive accelerated expansion, though at very different energy scales and rates. In the early universe, a high vacuum energy density produces a rapid inflationary phase that smooths and flattens space and then decays into a hot plasma. In the present universe, a much smaller vacuum energy density produces a gentle acceleration that shapes the large-scale fate of structures. This parallel suggests that vacuum energy and its quantum fluctuations are central not only to the earliest moments of the hot phase, but also to the behavior of the universe on its longest timescales. If dark energy is truly a cosmological constant, then the same term in the gravitational equations influences the first instance after inflation ends the current acceleration and the far future. If dark energy comes from a field that evolves over time, its potential may be related in some models to the potentials that govern earlier inflationary dynamics. In multiverse scenarios, the value of dark energy can vary from bubble to bubble, and the fact that it is small but non-zero in the observable universe becomes part of a wider pattern of vacuum energies in different regions. In cyclic or brain-based models, the component that now appears as dark energy can help control the approach to a future contraction or to a new collision linking the far future of one cycle to the conditions that set up the next. In these views, dark energy is not only a feature of the late universe, but also a bridge between the end of one phase and the beginning of another. Even in more conservative frameworks that avoid explicit cycles or multiverses, the existence of dark energy forces any proposed pre-Big Bang scenario to account for why vacuum energy has the value it does and how it behaves across different eras. A theory that describes the inflationary phase, the hot Big Bang, and the later evolution must also explain why the same equations that govern high-energy vacuum behavior in the early universe now appear in a much milder form in the present cosmos. In this sense, understanding dark energy is part of understanding what kind of background reality supports both the rapid expansion that may precede the Big Bang and the slow acceleration that shapes the fate of the universe long after. Modern cosmology does not test ideas about the early universe only with pen and paper. It uses a growing set of instruments that watch the sky and many bands of light map the positions of galaxies over huge volumes and listen for faint gravitational waves that ripple through space-time. Each new survey adds texture to the picture of what happened after the hot phase begins, and in doing so it constrains what could have been true before it. Satellites that measure the cosmic microwave background have already played a central role. By charting the temperature of the ancient glow across the whole sky, they reveal the almost uniform background and the tiny fluctuations that inflationary models predict. More detailed measurements of polarization, the preferred direction in which the waves of that light vibrate, carry additional information. Scalar perturbations, which are density variations, and tensor perturbations, which are gravitational waves, leave different patterns in the polarization. A particular swirling pattern called a B-mode is expected from primordial gravitational waves produced during inflation. Detecting such a pattern at the right strength and angular scales would give strong evidence that a rapid expansion phase occurred and would help fix the energy scale at which it took place. Current observations have measured polarization with high precision and have placed bounds on how strong any primordial gravitational waves can be, but they have not yet found a clear inflationary B-mode signal. This limits many models that predict large gravitational wave backgrounds while leaving room for others with weaker signals. Ground-based and balloon-borne experiments continue to push these limits by observing selected regions of the sky with ever greater sensitivity. At the same time, new proposals aim to map the cosmic microwave background even more finely, from space-reducing noise and foreground contamination to the point where very subtle features might become visible. If a primordial B-mode pattern is eventually detected, it would directly probe physics at energies close to the Planck scale, and would narrow the range of allowed scenarios for what the universe was doing just before the hot Big Bang. If, on the other hand, repeated measurements continue to find no such pattern, down to very low levels, that absence will favour models in which inflation occurs at lower energies, or in which alternative mechanisms generate the observed density fluctuations without a strong gravitational wave background. In both cases, the data would trim the space of possible histories, turning some speculative pictures of the pre-Big Bang era into ruled-out ideas and leaving others viable. Large-scale galaxy surveys complement background measurements by tracing how primordial fluctuations grow into structure. Instruments that measure redshifts for millions of galaxies build three-dimensional maps of where matter is located over a wide range of distances. The pattern of clustering in these maps, including the imprint of early sound waves known as baryon acoustic oscillations, depends on the spectrum of initial perturbations and on how the expansion rate changes over time. Comparing these maps with the predictions of inflation, cyclic models and modified gravity theories helps to check whether the same initial seeds inferred from the cosmic microwave background can account for the present web of galaxies. Weak gravitational lensing surveys, which track how light from distant galaxies is slightly distorted as it passes through the gravitational fields of intervening matter, provide another way to weigh the distribution of mass and to test how structure grows. Any mismatch between the inferred growth history and the expectations from a simple inflationary hot Big Bang model could hint at new physics that changes either the initial conditions or the law of gravity itself. Beyond photons, gravitational wave observatories open a different window. Ground-based detectors are sensitive to mergers of black holes and neutron stars in the nearby universe, but future space-based detectors and pulsar timing arrays aim to detect a background of gravitational waves from much earlier times. Some inflationary models, as well as certain bouncing or brane collision scenarios, predict a stochastic background of gravitational waves produced by processes in the early universe. The shape and strength of this background carry information about the energy scale and duration of those processes. A detection would not only extend the observational record further back, but would help distinguish between a simple single phase of inflation and more complex histories that involve multiple stages sharp features in the potential or violent transitions between vacua. New probes are also being developed to study the so-called dark ages of the universe, the period between the release of the cosmic microwave background and the formation of the first luminous sources. Observations of the hyperfine transition of neutral hydrogen at a wavelength of about 21 centimeters offer a way to map the distribution of matter during this era. Arrays of radio antennas on Earth and potentially on the far side of the Moon in the longer term can in principle measure how hydrogen absorbs or emits radiation against the cosmic background over a wide range of redshifts. This three-dimensional map would fill in the gap between the very early universe seen in the microwave background and the later universe seen in galaxy surveys. It would reveal how quickly the first structures form, how they heat and ionize their surroundings, and whether there are any unexpected features that point back to unusual initial conditions. Together, these observational efforts act as a series of cross-checks on the frameworks used to describe what came before the hot Big Bang. Inflationary models must not only explain the smoothness and flatness of the universe and the statistics of the background fluctuations, but also fit the detailed pattern of galaxy clustering gravitational lensing and any gravitational wave background that is observed. Cyclic and bouncing models must provide initial perturbations that match the measured spectrum and must navigate constraints on non-Gaussianity and on any residual signatures of a bounce. Brane-based scenarios have to account for how interactions in higher dimensions manifest as specific patterns in the lower dimensional sky. The multiverse idea, while often difficult to test directly, is also subject to indirect constraints. If it predicts typical universes that differ strongly from what is seen, it becomes less plausible as a description of reality. In practice, data and theory influence each other in a continuous loop. An anomaly in the cosmic microwave background, such as an unexpected alignment of large-scale modes or a region with lower power than average, can inspire new models or new variations on existing ones. Later measurements may confirm that the feature is real and significant, pushing theorists to seek a deeper cause, or may show that it was a statistical fluctuation or an artifact of observation. Likewise, a theoretical proposal about pre-Big Bang physics can lead to specific predictions such as a small oscillatory pattern in the power spectrum or a preferred direction in polarization. Observers can then design analyses to look for these signatures. Sometimes the search finds nothing pruning the idea. Sometimes it turns up hints that guide the next generation of models. As the reach of telescopes and detectors grows, the part of the cosmic history that is constrained by direct observation slowly expands. From a narrow window on galaxies in the nearby universe, cosmology has moved to a broad record that includes the background radiation, large-scale structure, and the acceleration of the present-day cosmos. With each new dataset, the allowed stories about what existed before the Big Bang become more sharply defined. Some possibilities are discarded because they cannot reproduce the observed sky, while others are reshaped to match the precise texture of the data. The very early universe remains hidden behind the limits set by the Planck era and by horizons, but the boundary between tested physics and speculation shifts as experiments improve, and the region close to that boundary is where ideas about pre-Big Bang phases are most tightly constrained. In everyday language, the word before suggests a familiar ordering of events, one moment giving way to another along a line of time. Applied to the universe as a whole, the same word becomes more difficult to interpret. The standard hot Big Bang model provides a clock that runs smoothly back from the present to a very early epoch measuring the age of the hot plasma, the formation of atoms, the birth of stars and galaxies, and the synthesis of light elements. Extrapolated far enough that clock reaches a point where the density and temperature become large, and the scale factor of the universe, the number that describes how big space is relative to its present size, tends towards zero. In the simplest reading of this model, that limiting point is labelled as time zero, and the age of the universe is defined as the time elapsed since that moment. Within this framework, asking what existed before the Big Bang appears to be asking about times with negative values on a clock that by construction starts at zero. General relativity refines this picture by tying time to the geometry of space-time. In this theory, time is not a separate stage on which events occur, but one dimension of a four-dimensional manifold whose curvature is set by energy and momentum. A Big Bang singularity in the classical equations marks a boundary where geodesics, the paths that free-falling particles follow, cannot be extended further back. At that boundary, the curvature becomes infinite and the mathematical description fails. One possible view is that this breakdown indicates a genuine beginning of time in the sense that there simply are no earlier events in the space-time described by the model. Another is that it signals the limit of that particular description, beyond which quantum gravity effects or additional dimensions must be taken into account. In that second view, the question of what existed before the Big Bang remains open, but it cannot be answered within the classical hot Big Bang framework alone. It requires a theory that tells how space-time behaves when quantum effects are strong, or when the familiar four-dimensional picture is only an approximation. Different theoretical proposals offer different ways of extending the story beyond the classical boundary. Eternal inflation describes a space-time in which a rapid expansion phase continues in some regions, while ending in others, producing bubbles that each undergo their own hot Big Bang-like transitions. In that setting, the Big Bang associated with one bubble has a well-defined meaning as the local end of inflation and the start of a hot phase, but the inflating background in which the bubble forms can stretch indefinitely into the past, along some world lines, and indefinitely into the future along others. The word before then refers to the state of the inflationary field and the geometry of the background region that later gives rise to the bubble. In brane collision models, the Big Bang on a given brane corresponds to a collision or close passage in a higher dimensional bulk. The time coordinate that labels events on the brain extends smoothly through the collision, and the question of what came before the Big Bang on that brain becomes a question about the previous motion of brains in the bulk, and about any earlier cycles of approach and separation. In cyclic and bouncing models, the hot phase is one part of a repeated sequence of contractions and expansions. The word before points to the preceding contraction during which fields and geometry evolve toward the conditions needed for a bounce. In quantum gravity scenarios where space-time and time emerge from more basic structures, the concept of before becomes more subtle. Near the Planck regime, the familiar time coordinate may lose its meaning, replaced by relational descriptions in which only correlations between observables are fundamental. In such approaches, what existed before the Big Bang may not be describable in terms of earlier and later at all, but instead in terms of a more abstract configuration of quantum degrees of freedom from which classical spacetime and its time coordinate arise. Multiverse frameworks add another layer. If the underlying theory admits many vacuum states with different effective constants, and if eternal inflation populates these vacua in different regions, then there is no single pre-Big Bang state in any global sense. Each bubble that contains a hot Big Bang phase has its own prior history in the inflating background and its own local field configuration. Some bubbles may form in regions where the inflationary energy scale is high, others in regions where it is low. Some may inherit parameters that permit long-lived stars and heavy elements, others parameters that do not. From this perspective, the question of what existed before the Big Bang in the observable universe is narrowed to the question of what the local patch of the inflating space was like before the transition that produced this particular bubble took place. The rest of the multiverse, with its other bubbles and perhaps other forms of matter and geometry, lies outside the observable domain and outside the backward light cone of any event in the present universe. Observationally, the only accessible clues about any pre-Big Bang phase are those carried forward into the hot era and preserved in the cosmic microwave background, the arrangement of galaxies and the behavior of the present expansion. Different models of what came before make different predictions for these traces. Inflationary models tie the spectrum of primordial fluctuations to the properties of the inflationary field and its potential. Bouncing models relate the same spectrum to conditions during contraction and to the mechanics of the bounce. Brain scenarios associate it with the details of higher dimensional dynamics. Quantum gravity approaches suggest possible imprints in the form of modified dispersion relations, non-standard gravitational waves, or small deviations from the simplest inflationary predictions. As measurements improve, some of these possibilities are disfavored because they fail to match the precise patterns seen in the sky. Others remain consistent and are adjusted to fit the data more closely. The region of theory space that survives these tests gradually shrinks, but it remains wide enough that several different types of pre-Big Bang histories are still compatible with current observations. In all of these discussions, the meaning of before is shaped by the mathematical structure of the model being used. In some time has a finite extension into the past along every path, and simply does not exist beyond a certain limit. In others, time continues through a bounce or a collision connecting the hot phase to an earlier contraction, or to prior activity in a higher dimensional bulk. In yet others, time emerges only as an approximate parameter at scales much larger than the Planck length, so that asking about times before a certain threshold is like asking about distances inside a region where the concept of distance has not yet formed. The observable universe provides boundary conditions that any of these models must satisfy, but it does not yet single out one meaning of before as correct. For the moment, the question of what existed before the Big Bang remains part of a conversation between theory and observation. The hot Big Bang phase is well established as a description of how the early plasma cools and structures form, and the evidence for some kind of earlier smoothing mechanism, such as inflation or a related process, is strong. Beyond that, the possibilities branch into inflating backgrounds, brane collisions, bounces, and emergent spacetimes. Each possibility offers a different answer to how far back time extends and what kind of physical state set the stage for the hot universe that later develops into galaxies, stars, and planets. As observations grow more precise and theories of quantum gravity mature, some of these answers may be ruled out and others refined, but the central question continues to point beyond the visible horizon and beyond the earliest directly tested moments toward a wider and still uncertain structure in which the Big Bang of the observable universe is one transition among others rather than an isolated and complete beginning.